Before describing the mathematical induction, let me introduce an example that will give you the idea of what induction is. First of all, induction is a method of proof, and it's going to be useful when we want to prove that something happens, let's say, always. And we are going to give more precision of what means always. But let's think in this example of the dominoes. You know that what happens if I push the first domino, right? So you know that all of them will fall. Well, let's suppose that we want to prove that all the dominoes fall, so that each of the dominoes fall. Well, one way to prove it would be to say, well, the first one falls, the second one falls, the third one falls, the fourth one falls, and so on. But then our proof will have an infinite number of steps, right? Because we will need to prove one by one that all falls. Well, induction gives us another way to prove it, in which we don't have to prove one by one. Since we know what had to happen for this domino to fall, right? So we know that without checking one by one, we know that all of them are going to fall if what? So let's think what are the conditions for all these dominoes to fall. Well, first of all, I had to push the first one, right? So that would be one condition. I mean, in order for them to fall, I need to push the first one. Otherwise, nothing is going to happen, right? All of them will be standing there. So the first condition is the first one has to fall. But then, what else have to happen? Imagine this queue here of dominoes. Even if you push the first one, it may be possible that not all of them fall, right? Suppose that, for instance, these two are to separate and prevent them all from falling. So what other condition we need to secure that all of them are going to fall? The first one have to fall, but what have to happen is that if we pick any one of the dominoes and this one fall, so the next one has to fall. Observe that is a compound statement what I am declaring here. I'm saying if one fall, the next one has to fall. And if this thing happens for all the dominoes, that is one falls, the next one falls, so then we are sure that the whole line of dominoes are going to fall. So we can express that saying, first what had to happen is that the first domino falls, and the second condition is that if one domino falls, then the next one falls. So if these two things happen, so then we are sure that all the dominoes until infinity are going to fall. Let's see how we express this principle in mathematical terms. So the idea is that we want to prove a proposition. So in this example, the proposition was the domino falls. So we want to prove some proposition that depend on n, where n is a natural number. And we want to prove that this proposition is true for all natural numbers greater or equal than 1. So it can be greater or equal than 3 or 20, but let's say in general we want to prove that this is true for all natural numbers greater or equal than 1. So is the first, for n equal 1 false, so we want to prove that all of them are going to fall. Okay, so how do we prove this? Well, the mathematical induction has two steps. One is called the basis step, in which we prove that P of 1 is true. That the proposition for the value of n equals 1 is true. That means the first domino falls. The second step is what is called the inductive step. And here we show that if the proposition is true for n equal k, we have to prove that the proposition is true for n equal k plus 1. That will be the equivalent to say that if one falls, so then the other one falls. So that will be n equal 1, n equal k, n equal k plus 1. Let's see how do we prove a statement, a proposition, a particular proposition by induction. In this example, we want to prove that the addition of these numbers 1 plus 2 plus 3 plus 4 plus 5 all the way until n is the same thing that actually multiplying n by n plus 1 and divided by 2. We want to prove that this is true always, for all values of n. That means that if I do this addition, for instance, for n equal 5 will be true, but if I do for n equal 20 will be true, for n equal 1 million will be true. It's always true that if you add these numbers, you obtain this. That's what I want to prove. That will be the proposition that depend on n. And I want to prove that no matter what n I put, this proposition will be always true for all n greater or equal than 1. Well, according with the induction method that we saw before, we have to prove first the basis step that will be to prove that this proposition is true for the first element here, which is n equals 1. So we have to prove first that for n equals 1, this equality is true. And what means that this equality is true for n equal 1? Well, you substitute in this formula n by 1. Be careful here that when you have this ellipsis here, what means is that this addition somehow is like stretchable and can be smaller, bigger, depending what n is. So, for instance, just this addition, if n equal 5, for instance, that will be 1 plus 2 plus 3 plus 4 plus 5, right? So that will be if n is equal 5. But if n is equal 3, will be just 1 plus 2 plus 3. That will be just for n is equal 3. You see that the n not only indicates the last number that you add, but also how long is the addition, right? So then when you substitute n by 1, you will do 1 plus nothing, because 1 is already the last one. So this is the value of the whole addition when you substitute n by 1. And then in the second side, that's easy to substitute. We just put a 1 in place of n, right? So that's as we got 1 times 1 plus 1 over 2. And then the inductive step, that's the most complicated step. The step is an if-then. So the step says that if this is true for n equal k, so then this is going to be true for n equal k plus 1. The idea is that this first part is the hypothesis. We know that this thing is true, and we want to prove, this is called the thesis, we want to prove that this is true. So this we don't know if it's true. We know that this is true, and the idea is, knowing that this is true, try to prove that this is true. So let's see how we're going to do this in this case. So first, the hypothesis is that this equality is true for n equal k. So we are going to substitute everywhere where we see an n, we are going to put a k, and so what we get is this equation here. So what we know is that this is true. The hypothesis is true. So we know is that we add the number from 1 to k, we obtain k times k plus 1 over 2. Now, the question is, the thesis, is this equality true when n is equal k plus 1? Well, we don't know. That is what we have to prove. The hypothesis, we know. The thesis, we don't. We have to prove it. So the thesis is then this equation, substitute instead of n, you are going to put k plus 1. And so by doing this, by substituting, we get this expression here. Observe that when we plug in here k plus 1 and k plus 1 is what I did here. K plus 1, k plus 1. And so we have the other one here and the 2 that are the remaining of the formula. So this is now the most important part of the induction. The idea is we have to prove this. We don't know if this is true or not. But we do know that this is true. So what we are going to do is start with this statement using that this is true and see if we can obtain the second part of the equality. See if we can actually prove that this red formula here is true. Then I start with this part. That's what is written here. And so I'm going to use this part. How do I use this part? Well, here is the addition of all the numbers until k plus 1. So that means 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus k and plus k plus 1. I mean that the one before k plus 1 is k. So we can express that there was k. So in other words, all this part here is exactly what appeared in the hypothesis of induction. So because of that, all this part can be substituted by this because we know that these two things are equal. So that is what I'm doing here in the second step. I'm saying all this is actually k plus 1 over 2 because I know that by hypothesis of induction. And now this second part here, I just copy as it is, right? So this first part was this, and this blue part I just copy as it is. Now the remaining here from this step to this is just the algebra. So these are two fractions. The way to add them is to do common denominator. That's what's done here. The common denominator between 2 and 1 is 2. So that's what expressed here, the common denominator. The new numerators are here k plus 1, just the same numerators that we have here. And for the last one will be this times 2. That is what is written here. This is just common denominator between these two fractions. From this step to this step, I just take as a common factor in these two terms. You see that there are two terms here that have a common factor that is k plus 1. Well, I took k plus 1 as a common factor and remains k plus 2. That is what is expressed here. We just look at the expression, and this expression is exactly what we have here. So we prove that this is actually equal to this. Then by mathematical induction, this means that this proposition that 1 plus 2 plus 3 plus n equals n plus 1 over 2 is true for all n greater than equal than 1. In other words, all the dominoes fall.